Every second, the sun fires a number of gravitons so large the human mind cannot picture it. They pass through walls, through planets, through you, and leave zero trace. We have built detectors the size of buildings. We have felt space itself ripple. We have mapped the leftovers of the Big Bang. And we still have never caught a single graviton. We will go inside the particle that holds gravity together, meet the machine that would collapse into a black hole the moment it turned on, and find out why the math of the universe refuses to add up. If you enjoy the ride, a like and subscribe keeps these coming. Now, we begin. Pick up any object near you, a phone, a pencil, a shoe. Now let it go. It falls every single time, no exceptions. Gravity is the most reliable force in the universe. You have trusted it your entire life without thinking about it once. But here's the problem. Scientists trust it too. They use it to map galaxies, predict orbits, and land rovers on Mars. The equations work perfectly at those scales. The math is clean, the predictions are accurate, and nothing breaks. Zoom in though. Zoom past the size of a cell, past the size of a virus, past atoms. Go all the way down to the smallest things physics can describe, the level of quarks and electrons, and pure energy packets. Down there, gravity completely falls apart. Every other force works at that scale. Electromagnetism, the force behind light and magnets, has a clean quantum theory. The strong nuclear force that holds atomic nuclei together has a clean quantum theory. The weak nuclear force behind radioactive decay has a clean quantum theory. Physicists spent decades building a framework called the Standard Model that unifies all three. It is one of the most tested and accurate scientific achievements in history. Gravity has no place in it. When scientists try to write gravity into quantum equations, the formulas spit out nonsense. Infinite values appear. Numbers that should shrink instead explode toward infinity and refuse to stop. The math does not just struggle, it collapses completely. This is strange because at large scales, gravity is the most dominant force in the universe. It holds stars together, it bends light around galaxies. It shapes the entire structure of space and time. Yet at the tiny scale where all other forces are understood, gravity becomes a ghost. It is there, you can measure its effects, but the rules that govern it at that scale remain completely unknown. Think about what that means. Physicists have a working theory for almost every interaction in nature. They can predict how electrons will behave, how particles will collide, how energy will move. But drop a single electron toward a single proton because of gravity, and the quantum math cannot describe what is actually happening at the fundamental level. Gravity wins the battle. Physics loses the argument. For over a century, scientists have known this gap exists. Einstein's general relativity, published in 1915, describes gravity as the curving of space and time itself. A massive object bends the fabric of the universe around it, and other objects follow that curve. The theory is elegant, and it works beautifully. GPS satellites require Einstein's corrections to stay accurate. His math has never failed a test at large scales. Quantum mechanics, developed in the early 20th century, describes the universe at the smallest scales as a world of discrete packets, jumps, and probabilities. It also works beautifully. Modern computer chips and lasers exist because of quantum mechanics. Two perfect theories, two completely different pictures of reality, and they refuse to combine. Every attempt to merge them produces those cascading infinities. Something in one framework is fundamentally incompatible with the other, and nobody has figured out what. The universe cannot actually work in two separate ways depending on size. There has to be one set of rules underneath everything. Physicists are certain of that. But finding those rules requires solving a problem that has stumped every brilliant mind for 100 years. The answer, many believe, starts with a single missing particle, And what comes next will show you exactly how strange that particle turns out to be. The universe runs on messengers. Every force you have ever experienced, every push, pull, or interaction between two pieces of matter happens because particles are flying back and forth between them, carrying the force like tiny packages. This sounds like science fiction, but it is the most tested idea in all of physics. Take light. When you flip a switch and a bulb lights up, electrons move and they send out photons. Those photons carry the electromagnetic force. When two magnets repel each other, photons are exchanging between them at the speed of light. You cannot see those photons, but they are the mechanism behind every electrical and magnetic interaction in the universe. Inside every atom, protons and neutrons are held together by a force so powerful it overpowers the electric repulsion between those protons. That force is carried by particles called gluons. Their job is pure binding, locking quarks together so tightly that no particle accelerator on Earth can fully separate them. Then there is radioactive decay. Certain atoms are unstable. Their nuclei break down over time and release energy. That process is governed by a force carried by particles called W and Z bosons. These particles are heavier than the atoms they work inside, which is why this force only operates at extremely short range. Three forces, three kinds of carrier particles, all confirmed, all measured, all precisely described by the Standard Model. Each carrier follows the same pattern. It is massless or nearly so. It travels at or near the speed of light, and it carries the force through space by exchanging between two objects, like a tennis ball bouncing between two players. The players feel a push. The tennis ball is the force carrier. Now think about gravity. Gravity pulls every object with mass toward every other object with mass. It works across trillions of miles. It bends starlight. It holds the moon in orbit. It is a real, measurable force affecting every piece of matter in the universe. By every rule of physics, it should have a carrier particle too. That particle is called the graviton. And unlike photons and gluons, scientists have never detected one, never measured one, never produced one in a lab. Every other carrier particle in the Standard Model has been confirmed through direct experiment. The photon was confirmed over a century ago. Gluons were confirmed in the 1970s. The W and Z bosons were confirmed in the early 1980s. The graviton remains, to this day, completely theoretical. This is a massive problem. If gravity truly behaves like the other forces at the quantum level, its carrier must exist somewhere. The math demands it. The logic demands it. A universe with three quantum force carriers and one mystery force does not make sense as a complete picture of reality. Scientists are not simply missing a particle the way you might misplace your keys. The graviton cannot be found with current technology at all, and the reasons why form one of the most fascinating chains of impossibility in all of science. Every instrument humans have built to probe the quantum world uses electromagnetic forces. Light, electrons, charged particles. Gravity is so extraordinarily weak at the quantum scale that none of those tools can touch it. The search for the graviton requires something new, something that does not yet exist, and the story of how scientists figured out just how impossible the search would be starts in 1934, with two physicists who named a ghost. In 1934, two Soviet physicists sat down and did something bold. They had no lab to confirm their idea, no instrument to detect what they were proposing. The technology to test their theory would not exist for another century, and even then it would fall short. But Dmitry Blokintsev and his colleague took everything they knew about force carrier particles and applied it to gravity. The result was the graviton, a name for a particle that had never been seen. At the time, quantum mechanics was still young. The photon had only recently been confirmed as a real particle. Scientists were just beginning to understand that forces were carried by particles at all. The idea that gravity might follow the same rules was a natural extension of everything physics was discovering. Blokhin and his colleague reasoned like this: if every force in nature operates through a carrier particle, and if gravity is a genuine force of nature, then gravity must have a carrier too. They worked out the basic properties this particle would need to have. They gave it a name, they published the idea, and then the world moved on, because there was absolutely nothing anyone could do to find it. Decades passed. Quantum field theory matured. The Standard Model took shape. Photons, gluons, W and Z bosons were all confirmed through experiments. Each discovery deepened the same uncomfortable question: where was the graviton? The naming of the graviton was an act of pure theoretical confidence. It said, the universe is logical. Forces obey consistent rules. Therefore, its carrier exists, even if we cannot touch it. That confidence has held up for 90 years. The graviton is still the leading candidate for the quantum carrier of gravity. Every major framework for unifying physics includes it. String theory mathematically demands it. No experiment has contradicted its existence, but no experiment has confirmed it either. This puts the graviton in a strange category of physics. Scientists treat it as almost certainly real. They write papers about its properties. They argue about its mass, its spin, whether it can decay. They build theories that require it to exist, and yet it sits completely outside the world of confirmed science. Imagine spending your entire career studying an animal that every expert believes exists, whose footprints appear everywhere, whose behavior shapes entire ecosystems, but that no human being has ever directly seen. That is the relationship physics has with the graviton. The particle was named, its basic properties were sketched out, and from that point forward, the question was never really whether the graviton existed. The question became whether humans would ever be capable of finding it. That answer required someone to actually do the math, to sit down and calculate precisely what kind of machine you would need to detect a single graviton. What would it cost? How big would it need to be? How sensitive? One man spent years on exactly that problem. His answer was not encouraging. It was not even achievable. His name was Freeman Dyson, and what he found waiting at the end of that calculation was something that bent the rules of physics itself. But before we get to his machine, you need to understand something about the graviton's most basic property, something that makes it unlike every other particle ever discovered. Its weakness is not just a technical problem, it is the deepest mystery in physics. Picture a perfectly smooth ball of pure energy, with no mass at all, flying through empty space at the speed of light. That is the basic picture physicists have of the graviton: massless, extremely fast, carrying the force of gravity from one object to another, the way a photon carries light. But the graviton has one feature that makes it unique among all known or predicted particles: its spin. Spin is a quantum property. All particles have it. Think of it like an internal rotation, though particles are not actually spinning the way a top spins. It is a deeper property tied to how a particle interacts with the forces around it. Physicists measure spin in whole or half numbers. Photons have a spin of 1. So do gluons, W bosons, and Z bosons. Every force carrier in the Standard Model has a spin of 1. That is part of what they have in common. The graviton is predicted to have a spin of 2, exactly double the other carriers. That single number is one of the main reasons scientists take the graviton seriously. When you write down the math for how a spin 2 massless particle would behave, the equations it satisfies are exactly the same as Einstein's equations for gravity. The match is precise. A spin 2 particle, by the rules of quantum field theory, would naturally produce gravitational effects. The math points directly to it. The graviton is also predicted to have zero electrical charge. It would not interact with the electromagnetic force at all. That is part of why it is so hard to detect. Every instrument humans use to study particles relies on electromagnetic interactions. Detectors work by measuring electric signals, photon emissions, or charge deposits. A particle with no charge and no mass leaves almost nothing behind. The graviton's properties also tell us about its range. Massless particles carry forces with unlimited range. The photon is massless, and electromagnetism reaches across the entire universe. The graviton, if massless, would also carry gravity across unlimited distance. That matches what we observe. Gravity does reach across the universe, weakening with distance, but never fully disappearing. Everything about the graviton's predicted description fits the force it is supposed to explain. That is encouraging. A particle does not often match a force so precisely by accident, but the spin 2 prediction comes with a catch. A spin 2 particle is more complex than a spin 1 particle. Its interactions are more intricate. When physicists try to build a complete quantum theory around it, the math becomes far messier than the clean frameworks used for photons or gluons. The equations for a spin 2 carrier do not simplify elegantly. They overflow with terms and complications. And when researchers push the calculations to extreme energies, those complications generate exactly the kind of infinite values that signal a broken theory. So the graviton's predicted shape makes perfect sense as a gravity carrier. The mass, speed, charge, and spin all line up. Yet the theory built around it refuses to be mathematically tamed. Scientists have a beautiful description of a particle. They just cannot write a complete theory for it without the math exploding. And the reason that math explodes connects directly to something about gravity you probably never considered before: how weak it actually is. The answer will change the way you see a fridge magnet forever. Walk into a kitchen, look at the refrigerator, grab a small magnet off the door, now hold that magnet above the floor, and let it go. It falls. Gravity wins. But now press that same magnet against the side of the fridge. It sticks, and it takes a small but definite effort to pull it back off. What just happened? A tiny magnet, maybe 2 inches wide, just competed with the gravitational pull of an entire planet. 6 septillion tons of rock, iron, and molten metal spinning in space for 4.5 billion years, pulled in one direction. Your little fridge magnet pulled in the other direction, and the magnet held its own. That tells you something extraordinary about how weak gravity actually is. Physicists have measured this carefully. Gravity is 10 to the 39th power times weaker than electromagnetism. To visualize that gap, if electromagnetism were as tall as the Empire State Building, gravity would be shorter than a single atom sitting next to it. The difference is so enormous that the human brain is not really built to process it. Every other force in nature operates at roughly similar strengths when compared to each other. The strong nuclear force and the electromagnetic force differ by a factor of around 100, which is large but manageable. The weak nuclear force is far smaller, but still operates within a world that quantum physics can describe. Gravity stands completely alone, separated from the others by a canyon so wide it breaks the unification of physics. This weakness has a name in physics. Scientists call it the hierarchy problem. Why is gravity so much weaker than every other force? Nobody knows. It is one of the deepest unsolved questions in all of science. The weakness matters for the graviton search in a very specific way. Force carriers interact through the force they carry. Photons interact strongly with charged particles because electromagnetism is strong. Detecting a photon is relatively straightforward. A single photon can kick an electron hard enough to produce a measurable signal. A graviton interacts through gravity, and gravity is almost 39 orders of magnitude weaker. The kick a single graviton delivers to any particle is so small that no instrument built from normal matter could ever register it. The signal would be buried under the vibration of the atoms in the detector itself. Thermal noise alone, the random jiggling of particles at room temperature, would drown out a graviton hit by a factor too large to calculate meaningfully. To catch a single graviton, you would need a detector so massive, so cold, and so isolated that the thermal noise drops below the graviton's signal. That requires conditions far beyond anything humans have engineered. How far beyond? One man sat down and worked out the exact numbers. He calculated the mass, the density, and the dimensions of a machine that could theoretically catch a single graviton. His name was Freeman Dyson. He was one of the most respected theoretical physicists of the 20th century, known for combining and clarifying other physicists' ideas into clear, testable frameworks. And when he finished his calculation, the machine he described was not just impractical, it was physically impossible in a way that no amount of engineering progress could ever fix. Spin sounds simple. In ordinary life, it means rotation, a basketball spinning on a finger, the Earth spinning on its axis. Spin means something is turning. In quantum physics, spin means something different. Every particle has spin as a built-in property, like a label it carries forever. But particles are not actually turning. Spin is a quantum number that describes how a particle interacts with everything around it. It determines how the particle looks when you rotate it mathematically, and what kind of force it can carry. Think of it this way: a particle with spin 1 looks the same after a full circle rotation. A particle with spin 2 looks the same after only half a rotation, 180 degrees. That difference changes everything about how the particle behaves in equations. Every confirmed force carrier has spin 1. Photons carry electromagnetism. Gluons carry the strong nuclear force. W and Z bosons carry the weak nuclear force. All spin 1. That is a pattern so consistent across the standard model. The graviton breaks the rule. It is predicted to have spin 2. And this prediction does not come from guesswork. It comes from matching the particle to the force. Einstein's general relativity describes gravity using equations that involve tensors, mathematical objects that carry two indices, two directions at once. When physicists worked out what kind of quantum particle would naturally reproduce those tensor equations, the answer was a massless spin 2 particle. The math pointed precisely to spin 2, and it pointed there from two completely different directions, both from analyzing the structure of general relativity and from purely quantum field theory arguments. The spin 2 prediction is one of the strongest theoretical clues in all of physics. It means that if any spin 2 massless particle exists at all, it would automatically produce gravitational behavior. The link is not assumed. It comes from the mathematics. Here is where it gets strange. In quantum field theory, the higher a particle's spin, the more complex its interactions become. Spin 1 particles already require careful mathematical treatment. Spin 2 particles generate equations that grow far faster in complexity. When physicists build a theory around a spin 2 gravity carrier and push those equations to high energies, the infinities appear, faster and more violently than in any spin 1 theory. In 1985, 2 physicists ran those calculations as precisely as they could. They were not trying to disprove the graviton. They were trying to see how badly the math broke at high energies. Their result was clear. Combining a spin 2 carrier theory with quantum mechanics produced infinities that could not be removed by any known technique. This is a specific technical failure. In quantum electrodynamics, the theory of the photon, infinities also appear. But physicists developed a method called renormalization to absorb them into the measured values of charge and mass. The technique works. The theory survives. For the spin 2 graviton, renormalization fails. The infinities multiply faster than the technique can absorb them. A new infinity appears at every energy level you test. The theory breaks in a way that cannot be repaired with existing tools. The spin of 2 is both the best clue that the graviton exists and one of the main reasons a complete theory of quantum gravity has never been written. And what the math collapses into when you try hard enough is even more unsettling than a simple failure. Atoms are made of protons and neutrons, protons and neutrons are made of quarks. Quarks, as far as scientists can tell, are not made of anything smaller. Most things in the universe have parts, structure, layers you can peel back. Physicists spent the entire 20th century peeling back those layers, and each time they found something smaller hiding inside. The graviton has no inside. It is what physicists call an elementary particle. That means it is a fundamental unit of nature, with no internal structure. You cannot cut it, you cannot smash it into pieces, and find smaller bits inside. The graviton is not built from components the way a brick is built from atoms. It is a single, irreducible thing. But calling it a particle is almost misleading because the picture of a tiny hard ball rolling through space does not capture what a graviton actually is. A better picture comes from fields. The universe is filled with fields, invisible layers of energy spread across all of space. The electromagnetic field fills the entire universe. The gravitational field does too. Every object with mass creates a dip in the gravitational field around it, and other objects respond to that dip. At the quantum level, these fields do not change continuously the way a smooth surface bends. They change in jumps, in discrete steps. The smallest possible jump in the electromagnetic field is a photon. One photon is the minimum amount by which electromagnetic energy can change. The graviton is the same idea applied to the gravitational field. It is the minimum possible change in gravity, the tiniest ripple the gravitational field can make. One graviton represents the smallest unit by which gravity can be transferred from one object to another. You cannot have half a graviton. Half a graviton would mean half the minimum change in a gravitational field, which quantum mechanics forbids. The field changes in whole steps only, and the graviton is the name for one step. This is why the graviton is described as a fundamental excitation of the gravitational field. Excitation means a jump to a higher energy state. One graviton is one jump. Billions of gravitons firing together produce the gravity you feel when you sit in a chair or watch something fall. Every time you see an object fall, physics says an enormous number of gravitons are being exchanged between that object and the Earth, each one carrying a tiny packet of gravitational interaction. The result of all those packets adds up to the smooth, continuous pull you observe. The individual packets, though, are so vanishingly small that even the most sensitive detector ever built cannot register them. Here is a way to feel the scale. A single gravitational wave, the kind that bends space enough for a detector on Earth to measure, carries roughly 10 to the 44th power gravitons. That is a number with 44 zeros. And that wave, enormous by any quantum standard, moves the mirrors in a detector by less than the width of a single proton. One graviton is unimaginably smaller than that. So the question of detection is not just a matter of building a better microscope or a more sensitive sensor. The particle is real, the theory says. The signal exists. But the signal is so faint it falls below any physical measuring process that nature permits. Freeman Dyson understood this better than almost anyone. And when he calculated what it would actually take, the machine he described was so extreme it stopped being a detector and became something else entirely. Freeman Dyson spent his life making the impossible seem manageable. He worked on nuclear-powered spacecraft. He calculated the energy needs of entire civilizations. He once proposed wrapping a shell around an entire star to capture its energy. He was not a cautious thinker. He was the kind of physicist who started with a wild idea and worked the math until he found out whether nature allowed it. In 2013, Dyson turned that same approach onto the graviton. He wanted to know precisely and honestly what a real graviton detector would look like. He followed the physics wherever it led. The logic started simply. To detect a graviton, you need a particle to absorb it. The graviton is so weakly interacting that it almost never hits anything. So you need an enormous number of target particles, billions upon billions of atoms, packed into the most dense material possible, cooled to near absolute zero to eliminate the noise from random atomic vibrations. How many atoms? Dyson ran the numbers carefully. To have even a reasonable chance of catching a single graviton in a practical time frame, your detector would need a mass roughly equal to the planet Jupiter. That is a mass 300 times greater than Earth, a sphere roughly 90,000 miles across. The material would need to be denser than Jupiter itself to improve detection probability, meaning something like a collapsed stellar object, neutron star density material, packed into a structure large enough to function as an instrument. Every part of this description exists outside human engineering by many orders of magnitude. The largest particle detectors ever built weigh tens of thousands of tons. Jupiter weighs 2,000 quadrillion tons. The gap between current technology and a functional graviton detector is not a matter of decades of progress. It is a gap that no roadmap in physics or engineering could plausibly close. Dyson was not surprised by this. He had done enough extreme calculations to expect extreme answers. What surprised him came next. When he looked more carefully at his detector, he realized the problem was worse than just size. A detector with the mass of Jupiter would create a gravitational field of its own. An enormous one. The machine would not just sit there passively waiting for gravitons. It would begin to compress under its own gravity, pulling itself inward with a force that no known material could resist. And the calculations showed that the detector, built to the specifications required to catch even one graviton, would be so massive that it would collapse under its own gravity before it could record a single measurement. A machine enormous enough to detect the smallest particle of gravity would be destroyed by gravity itself. Dyson described this result plainly. He concluded that a graviton detector, as physics currently allows, cannot exist as a functioning instrument. The physics of gravity prevents the detection of its own quantum particle. The trap was perfect, and the trap was built into the laws of nature. There was no workaround. But Dyson's collapse problem was only the first obstacle. Even if the machine somehow survived, the universe had a second defense ready. And that defense fills all of space, passes through everything, and outnumbers the stars. The image is worth sitting with for a moment. You have built the most ambitious scientific instrument in history. A sphere the mass of Jupiter, packed with the densest material known to physics, cooled to nearly absolute zero, every atom held in precise alignment, every vibration suppressed. The instrument is ready, and then gravity turns it off. A mass that large, sitting in space, does not hold itself together. Gravity pulls inward on every atom in the structure simultaneously. The force is proportional to mass, and the mass here is immense. The material presses inward from every direction at once. There is no container in the universe strong enough to hold it. No exotic material, no force field, no engineering solution addresses this, because the crushing force comes from the mass of the detector itself. When an object's mass becomes concentrated enough, gravity wins completely. The object collapses into itself, passing through a critical threshold where escape velocity, the speed something would need to travel to escape the object's gravity, exceeds the speed of light. At that point, nothing can leave. Space curves so tightly that even light bends back inward. The detector becomes a black hole. Dyson calculated that a detector massive enough to register even one graviton would cross this threshold automatically. The mass required for detection and the mass required to collapse into a black hole are, by the laws of physics, nearly identical values. You cannot build the detector without building the black hole. They are the same object. This is not an engineering problem. It is a fundamental one. The act of constructing a graviton detector, following every step the physics demands, produces an object that destroys itself and erases any measurement it might have taken. A black hole absorbs everything that falls into it. Any graviton the detector managed to catch would be swallowed by the detector's own singularity the moment the collapse began. The signal, if it ever existed, would vanish into the most information-destroying object in the universe. There is a sharp irony in this result. The graviton is the quantum particle of gravity. The only instrument large enough to catch a graviton would be killed by gravity. The particle cannot be detected because the detector becomes a victim of the very force it was built to study. Physicists call results like this a physical impossibility, not an impracticality. An impractical machine is one you cannot build with today's technology, but might build in the future. A physically impossible machine is one that the laws of the universe itself prevent from working, regardless of technology or time. The graviton detector, as currently understood, is physically impossible. And yet, even if somehow a version of this machine existed, even if some future physics solved the collapse problem with tools we cannot imagine today, the universe is not empty. It is filled with a constant flood of particles that pass through everything, hit nothing, and drown out any signal you are trying to read. Dealing with them makes the collapse problem look like a minor inconvenience. Imagine trying to hear a single whisper in the middle of a stadium packed with 100,000 screaming fans. Now imagine the screaming never stops, day and night, forever, coming from every direction at once, passing through the walls, through the floor, through your body. Impossible to block, impossible to filter, impossible to escape. That is what neutrinos do to any attempt at graviton detection. Neutrinos are particles produced in enormous numbers by stars, by supernovae, by radioactive decay, by the Big Bang itself. Every second, around 65 billion neutrinos from the Sun pass through every square inch of your body. You do not feel them because they interact with regular matter almost never. They pass through the entire Earth the way light passes through glass. A Jupiter-sized detector, even if it solved the collapse problem, would be bombarded by neutrinos constantly. Those neutrinos would occasionally interact with the detector's atoms, leaving signals, false alarms, noise. Dyson calculated the ratio of neutrino hits to graviton hits for a detector of that size. To detect a single graviton, the machine would have to sort through roughly 10 to the 34th power neutrino collision events. That is a 1 followed by 34 zeros. To put that in perspective, there are estimated to be around 10 to the 80 power atoms in the observable universe. The ratio of neutrino noise to graviton signal is far more extreme than comparing one atom to every atom in the universe. It is a gap that makes even astronomical comparisons feel inadequate. There is no known filtering method that can separate one graviton signal from 10 to the 34th power neutrino events. The signals are different in nature, but the graviton's fingerprint is so faint that no statistical technique, no matter how advanced, could confidently pull it from that background. This is the second wall. The collapse problem means the detector destroys itself. The neutrino noise problem means that even a hypothetically indestructible detector would be completely blind to what it was built to find. Both problems exist independently. Both are insurmountable with known physics. Together they form a double barrier that the graviton sits safely behind, completely shielded from human observation, not by accident, but by the structure of the universe itself. Physicists have described this situation with a phrase that captures the frustration precisely. The graviton is theoretically accessible, but physically immune to detection. It exists in a category all its own, more certain than many unconfirmed particles in its theoretical grounding, and more untouchable than any of them in practice. The universe designed a particle that carries one of its four fundamental forces, and then designed that same particle to be completely invisible to the civilization living inside that force. Some scientists found this troubling. Others found it fascinating. A few decided that if you cannot detect the particle directly, maybe you could approach it from a completely different angle, like watching the universe itself ripple and then working backwards from the wave toward the particle that should have made it. In 2015, that idea produced the most dramatic experimental result in a generation. And the story of what happened, and what it actually proved, is stranger than most people realize. Two of the greatest theories ever written hate each other: general relativity Einstein's description of gravity treats space and time as a smooth, continuous fabric. The fabric bends, it stretches, it curves around mass, but it never jumps or skips. It changes smoothly and predictably, like water flowing in a river. Quantum mechanics treats the universe as a place where everything comes in discrete chunks: energy, charge, spin, momentum. All of these come in minimum units. Nothing is truly smooth. Everything jumps in small but definite steps: smooth versus chunky, continuous versus discrete. These two descriptions of reality cannot both be correct at the deepest level. One of them, or possibly both, must be incomplete. For most of physics, this conflict stays hidden. General relativity handles large scales beautifully. Quantum mechanics handles tiny scales beautifully. They never need to overlap in practical calculations except in two places: black holes and the Big Bang. At both locations, matter is compressed so densely that both theories apply simultaneously, and at both locations, the combined math fails completely. In 1985, two physicists decided to test exactly how badly the math breaks when you try to write gravity as a quantum field theory. They worked through the calculations at what physicists call one-loop and two-loop levels, which means they calculated what happens when quantum corrections are applied to the gravity equations at increasing levels of precision. At one loop, infinities appeared, manageable ones, the kind that appear in other quantum field theories and can sometimes be absorbed using renormalization techniques. At two loops, the infinities were worse, far worse. Uncountably many new infinite terms appeared that could not be removed by any known method. The calculation showed that a quantum theory of gravity based on the graviton would require an infinite number of free parameters to be defined by experiment before it could make any predictions. A theory with infinite free parameters makes no predictions at all. It is mathematically empty. This result did not prove the graviton does not exist. It proved that physicists do not yet have the right mathematical framework to describe it. Somewhere in the structure of quantum mechanics or general relativity or both, there is an assumption that is either wrong or incomplete. Something is missing that would make the infinities cancel instead of explode. Finding that missing piece is the central unsolved problem in theoretical physics today. It has consumed the careers of thousands of brilliant researchers across 60 years. String theory is the most famous attempt to solve it. Others include loop quantum gravity, causal set theory, and approaches based on quantum information. All of them are trying to find the mathematical language that can describe what happens when gravity goes quantum without the numbers running off to infinity. None of them have fully succeeded yet. The math breaking is, in a strange way, more informative than a clean result would be. It tells you precisely where your understanding ends. And the fact that gravity breaks quantum math at the two-loop level points to something deep. The relationship between space, time, and quantum reality is more complex than anything physicists have written down so far. Something fundamental is missing. And the strangest clue to what that something might be came from an observatory buried underground in Louisiana, listening for the ripple of two black holes that collided over 1 billion years ago. On September 14, 2015, at 5:51 in the morning Eastern Time, two detectors registered a signal. It lasted 0.2 of a second. It was a chirp, a rising frequency spike, the kind of sound a physics textbook would describe as the merger of two massive objects. The detectors were the Laser Interferometer Gravitational Wave Observatory, a pair of facilities positioned in Louisiana and Washington state, each built as an L-shaped tunnel stretching 2.5 miles in each direction. The signal matched the predicted output of two black holes, each several times the mass of the Sun, spiraling into each other and merging over 1 billion light-years away. Space itself had rippled, and the ripple had traveled for more than 1 billion years across the universe and moved the mirrors inside those detectors by a distance smaller than 1/10,000th the width of a proton. The achievement was extraordinary. A century after Einstein predicted gravitational waves existed, humans had built an instrument sensitive enough to feel one. Every person involved in the project had spent years, in some cases decades, working toward a detection that many believed would never come. The measurement confirmed something enormous. Gravity propagates as a wave. Space and time deform. Those deformations travel outward from their source, and those traveling deformations carry energy. Einstein was right, but here is what the detection did not do. It did not detect a graviton. A gravitational wave is an enormous thing. The wave detected in 2015 carried roughly 3 solar masses worth of energy, the equivalent of 3 suns converted entirely into gravitational radiation, in less than a second. That wave contained an almost incomprehensible number of gravitons, somewhere around 10 to the 44th power. Measuring that wave is like measuring the height of a tsunami. Powerful, dramatic, and informative, but it tells you nothing about the individual water molecules making up the wave. The graviton is one water molecule. The gravitational wave is an entire ocean. Detecting the wave proved that gravitational radiation exists and travels at the speed of light, which matched the graviton's predicted behavior. Precisely. That is real, meaningful support for the theory, but it remains indirect evidence, the shadow of a particle rather than the particle itself. Physicists were careful to say this clearly. The detection confirmed the wave. The particle behind the wave remains undetected. What it did open was a new era of gravitational wave astronomy. In the years following that first detection, dozens more events were recorded. Black hole mergers, neutron-star collisions, and signals from sources previously invisible to any telescope. Each one gave physicists more data about how gravity behaves at cosmic scales. And hidden somewhere in all that data, some researchers began to wonder, might be the faintest traceable fingerprints of the quantum nature of gravity. Not the individual graviton, but patterns in how gravitational waves travel and interact that might hint at what the graviton is doing underneath. That search is still ongoing. The results so far are ambiguous, and the gap between a detectable wave and an undetectable particle is even wider than most people imagine. Picture yourself standing on a beach. A wave rolls in from the ocean, lifts you off your feet, and pushes you 20 feet up the shore. You felt that. Your body registered it. You measured it with every nerve ending in your body. Now someone asks you to identify one specific water molecule from that wave, one single H2O unit from the billions of tons of water that just knocked you over. Not where the wave came from, not how fast it traveled, one molecule. That is the gap between detecting gravitational waves and detecting a graviton. The gravitational wave detectors that caught the black hole merger signal in 2015 are sensitive enough to measure a distance change smaller than 1/10,000th the width of a proton across a tunnel to an A, half miles long. That sensitivity is already the most precise measurement in human history. Engineers spent decades developing mirror coatings, laser systems, and vibration isolators to reach it. And it is still roughly 30 orders of magnitude away from being able to register a single graviton. 30 orders of magnitude means a factor of 1 followed by 30 zeros. Improving a detector by 30 orders of magnitude is not a matter of building a better version of the same machine. It would require a completely new type of physics that does not yet exist. The difference in scale between the wave and the particle is actually intuitive once you sit with the numbers. A gravitational wave involves astronomical amounts of mass, converting to energy in a fraction of a second. The wave that reached Earth in 2015 originated from a collision releasing more energy than all the stars in the observable universe combined for those brief moments of merger. All of that energy, spread across space for over 1 billion years, produced a signal so faint it moved a mirror less than the width of a proton. One graviton produces a force incomparably smaller than that. There is no instrument currently proposed, planned, or theoretically conceivable that bridges this gap directly. Dyson's analysis closed the door on direct detection. The The wave detectors confirmed gravity's wave behavior, but left the particle untouched. So physicists began looking for other paths. If you cannot catch the raindrop, can you read the cloud? That question pushed a group of experimental physicists in a direction nobody expected, away from outer space and into a tiny slab of semiconductor, cooled to the edge of absolute zero. What they found there in 2024 surprised the entire field. The Sun is 93 million miles away. Every second it converts about 4 million tons of mass into pure energy. Through nuclear fusion, that process releases enormous numbers of photons, the particles of light and heat that warm the surface of every planet in the solar system. And according to physics, it also releases something else, something you will never feel. Physicists estimate the Sun radiates approximately 10 to the 24th power gravitons every second. Written out fully, that is a 1 followed by 24 zeros. Every single second, continuously, around the clock, those gravitons travel outward from the Sun at the speed of light. They spread through the solar system and beyond, growing more spread out as they travel, following the same inverse square law as light. After 93 million miles, they reach Earth, and they pass through it. Gravitons interact with matter so weakly that the entire mass of the Earth is essentially transparent to them. The planet does not stop them, slow them, or absorb them in any meaningful quantity. They continue outward into deep space. As you listen to this, gravitons from the Sun are passing through you, not one or two, an incomprehensible number every second, flowing through your body the same way they flow through the ground, through buildings, through the planet itself. You will never feel a single one. No instrument you will ever use will detect them. They carry the force of gravity, that same force holding you to the ground, and yet each individual graviton interacts so feebly with matter that it might as well not be there. This is one of the sharpest illustrations of gravity's weakness at the quantum scale. The Sun, a nuclear furnace more than 1 million times the volume of Earth, pours out gravitons in quantities that dwarf the stars. And humanity, sitting in the middle of that graviton rain, remains completely blind to it. There is something strangely beautiful about that picture. The universe constantly broadcasting its most fundamental particle at a rate beyond any human scale to a species that cannot build a receiver. But a falling apple brings it closer to home. The next time you watch something drop, physics says something specific is happening at the quantum level between that object and the Earth. Something you have never seen, but that the universe insists is occurring trillions of times every microsecond. An apple falls from a tree. You have seen this 1,000 times. The fruit pulls free, drops a few feet, hits the ground. Simple, familiar, completely unremarkable. But quantum physics, if it applies to gravity the way it applies to everything else, says something specific is happening during that fall that no human eye has ever witnessed. Trillions of gravitons are firing every microsecond between the apple and the Earth. Each one is a tiny quantum of gravitational interaction, an exchange of force at the most fundamental level. The apple and the Earth are not connected by a smooth, invisible thread. They are, according to the graviton model, being continuously peppered by a storm of particles so faint they pass through everything without leaving any detectable trace. The total effect of those trillions of exchanges is the smooth acceleration you observe. The apple speeds up at a rate of 32 feet per second squared as it falls. That smooth curve is the averaged result of countless tiny quantum events stacking up. This is how every quantum force works. The apparent smoothness of a magnetic field is actually billions of photons flying back and forth between charged objects every second. The apparent smoothness of a nuclear interaction is gluons constantly exchanging between quarks. The smooth appearance is always the large-scale average of something happening in discrete packets at the quantum level. Gravity appears smooth. Einstein's equations describe it as smooth. Space curves smoothly around mass. And yet, if the graviton exists, That smoothness is an illusion at the smallest scales. Underneath, the same kind of quantum storm is happening. Every time you hold two magnets near each other and feel the repulsion, photons are causing that push. You cannot see or detect individual photons with your bare hands, but the force is real, and the particle behind it is real. The Graviton picture says the same is true for every falling object, every orbit, every gravitational attraction in the universe. The force is real. The particle behind it should be real. You just live at scales too large to see the individual packets. The apple does not know it is participating in a quantum process. Neither do you when gravity holds you to the ground. But the equations say it is happening constantly, everywhere, for every object with mass in the universe. This idea that familiar gravity is secretly a quantum process hidden behind smooth appearances is one of the reasons physicists find the graviton so compelling. The logic is almost airtight. Almost, because the same logic that makes the graviton theoretically necessary also led a physicist to propose something that shook the entire foundations of where gravitons might actually be going. What if they were not staying in our universe at all? Every force carrier known to physics stays in our universe. Photons travel through our 3 dimensions of space and 1 dimension of time. Gluons stay in our universe. W and Z bosons stay in our universe. Their interactions, their effects, their entire existence plays out in the 4 dimensions we can observe. String theory says the graviton does something completely different. String theory is a framework that attempts to unify all of physics by describing every particle as a tiny vibrating loop or strand of energy, rather than a simple point. The length of these strings is smaller than anything humans can probe, and their vibration pattern determines what kind of particle they create. In string theory, most particles are open strings. They are strands with 2 free ends, and those ends are attached to surfaces called branes. A brane is a dimensional surface, like a sheet, but extended through multiple dimensions. Our entire universe in this picture is a brane. Everything we can see or touch exists on the surface of that brane. Open strings cannot leave the brane. Their ends are stuck to it. That is why photons, gluons, and all the other particles stay in our universe. They are open strings anchored to our 3-dimensional surface. The graviton is different. String theory predicts the graviton is a closed string, a loop with no free ends. A loop has nothing to anchor it to the brane. It can detach from our dimensional surface and drift into the higher dimensional space surrounding our universe. String theory generally requires 10 or 11 total dimensions to be mathematically consistent. The extra dimensions beyond our 4 are thought to be curled up at an incredibly small scale, too tiny for any current instrument to detect. But they are there in the theory, and the graviton, as a closed string, can travel through them. Every other force is trapped on our brane. Gravity leaks out. This single idea explains one of the deepest mysteries in physics with one sentence. Gravity appears so incredibly weak in our universe because most of it has already leaked out. The gravitons carrying the gravitational force do not stay where we can feel them. They drift into hidden dimensions, and only the small fraction that remains in our universe produces the gravity we experience. The fridge magnet, competing with the gravity of the entire Earth, suddenly makes sense. The Earth's gravity is not as strong as it could be. Gravity's full strength is spread across hidden dimensions we cannot access. We feel only what leaks back. This is a theory built on a framework that has never been directly confirmed, but the explanatory power is striking. One assumption, that the graviton is a closed string, resolves the hierarchy problem that has puzzled physicists for decades. And if the graviton can leak into higher dimensions, there is a follow-on prediction that is even stranger. If gravity leaks out, maybe some of it can leak back in, from angles and directions that standard physics says should be empty. The fridge magnet problem has bothered physicists for a long time. Gravity shapes the universe at the largest scales. It holds galaxies in formation. It controls the orbits of planets, and the paths of light around black holes. Over distances of billions of light years, gravity is the dominant force shaping everything you can see. Yet on the scale of a proton, gravity is 10 to the 39th power times weaker than electromagnetism. That gap is so extreme it strains credibility. Why would a force be simultaneously universe-shaping and almost immeasurably weak at small scales? Standard physics has no answer. The Standard Model has no mechanism that explains why the gravitational force coupling constant is so much smaller than the other forces. It is simply a number physicists measure and plug into equations. Where it comes from remains unknown. String theory with extra dimensions offers a specific mechanism. When you turn it on, water shoots outward in 3 dimensions, spreading in all directions equally. The water pressure at the sprinkler is strong, but 20 feet away from the source, the water has spread so far through space that only a tiny fraction hits any single spot. The pressure drops. Now picture a garden hose instead. The water is forced into a narrow tube. All the pressure stays concentrated. At 20 feet, the pressure is almost the same as at the source. The force does not dilute because it has nowhere to spread. In our universe, gravity behaves like a sprinkler, spreading into many more dimensions than we can see. Gravity dilutes across extra dimensions because the graviton, as a closed string, can move through them. By the time the gravitational effect reaches the scales we measure in laboratories, it has spread through all those extra dimensions and lost most of its strength. The other forces behave like the garden hose. Open strings stuck to our brain cannot spread into extra dimensions. Electromagnetism, the strong force, the weak force, all stay concentrated in our 4 dimensions. Their strength does not dilute. The result? 4 forces operating in the same universe, 3 of them concentrated in 4 dimensions, and 1 of them spreading across 10 or 11. The concentrated ones feel strong, the spreading one feels weak. The hierarchy problem dissolves. This prediction can actually be tested in principle. If extra dimensions exist and gravitons leak into them, then at very short distances, gravity should start to behave differently. Close enough to the extra dimensions, their presence would change how fast gravity weakens with distance. At normal scales, gravity follows an inverse square law, weakening with the square of distance. At scales close enough to the size of the extra dimensions, it should weaken faster. Experiments have tested gravity down to distances shorter than the width of a human hair. So far, the inverse square law holds. Either the extra dimensions are smaller than the current experimental reach, or they do not exist in the form string theory predicts. The search continues, and while some physicists spent decades pursuing extra dimensions through theory and tabletop experiments, a different group of researchers went underground with a very different machine. They cooled a flat plate of semiconductor material to near absolute zero, turned on a powerful magnetic field, and watched what the electrons inside did next. What they saw in 2024 changed what scientists believed was achievable in a laboratory. A laboratory in a university basement is not where most people expect a breakthrough in quantum gravity to happen. No telescope, no particle accelerator miles long, no detector the size of a stadium, just a flat plate of material smaller than a playing card, a powerful magnetic field, and a refrigerator cold enough to stop almost all atomic motion. In 2024, a team of physicists ran an experiment using a semiconductor called gallium arsenide. This material is already used in everyday technology, laser pointers, solar cells, and high-speed electronics. But cooled to temperatures near absolute zero, around 459 degrees below 0 Fahrenheit, it behaves in ways that normal physics cannot describe. The team applied a powerful magnetic field perpendicular to the plate. At those temperatures, and under that field strength, the electrons inside the material could no longer move independently. They were forced into a collective state, where every electron's behavior became linked to every other electron's behavior. The entire electron population moved as a single coordinated system. Physicists call this a fractional quantum Hall state. It is one of the most exotic phases of matter known to science, and it can only exist when you strip away almost all thermal energy and apply exactly the right field conditions. Inside that collective electron state, the team looked at how the electrons were vibrating. Vibrations in a quantum system come in discrete modes, each with its own energy and quantum properties. The team measured the spin of those vibrations. The dominant vibration mode had a spin of 2, a spin 2 collective excitation, massless in its behavior, propagating through the material at a fixed speed. The mathematical description of what the electrons were doing matched the theoretical description of a graviton with a precision that surprised the researchers themselves. They called it a graviton-like excitation, careful wording, deliberately cautious. Because what they had found was not a particle of gravity. Gravitons arise from the gravitational field. These excitations arose from electrons in a magnetic material. The underlying physics is completely different. What the experiment demonstrated was something more specific and, in its own way, more useful. It showed that the quantum properties scientists assigned to the graviton, the spin 2 behavior, the massless propagation, the specific interaction signatures, are not just theoretical constructs invented for convenience. They appear naturally in a real physical system under the right conditions. When a theoretical prediction shows up unsolicited in a completely unrelated system, it suggests the prediction is pointing at something real. The mathematics is not arbitrary. The universe independently produced something that looks exactly like what the equations describe. For researchers working on quantum gravity, this was meaningful. The graviton had been a mathematical object, a necessary piece of the equations. Now there was a physical system that demonstrated the same behavior. A mirror, not the thing itself, but a mirror that reflects a very specific shape. The semiconductor result cannot detect gravity. It cannot catch an actual graviton. It cannot probe the gravitational field in any way. The electrons in gallium arsenide are responding to magnetic and electric forces, not gravitational ones. But it opens something new. If spin 2 excitations can emerge in condensed matter systems, physicists can study their properties in the lab, something they could never do with real gravitons. They can probe how spin 2 quanta interact, scatter, and decay. They can test theoretical predictions about graviton behavior using a system they can actually control. The ghost finally had a shadow, and what the shadow looked like raised a question nobody had seriously considered before. What if the graviton is not quite what everyone assumed it to be? The 2024 experiment made headlines. Physics communities spent weeks discussing what it meant. Some descriptions called it the first observation of a graviton. Others were more careful. The careful ones were right. What the experiment found was a collective excitation of electrons that shares mathematical properties with the graviton. The spin 2 signature was real. The behavior matched the theory, but the electrons in a semiconductor chip and the gravitational field of the universe are two entirely different things. Think about it this way. Sound waves in air and electromagnetic waves share many mathematical features. Both can be described by wave equations. Both carry energy. Both have frequency and amplitude. But a sound wave is atoms bumping into each other. An electromagnetic wave is oscillating electric and magnetic fields. Same mathematical description, completely different physical origin. The graviton-like excitation in the semiconductor experiment is closer to the sound wave side of that comparison. It shares the math, not the physics. The electrons were responding to a magnetic field, not to the curvature of spacetime. The excitation propagated through matter, not through the fabric of the universe. The spin 2 behavior emerged from a collective quantum state, not from the gravitational field itself. For a confirmed graviton, you would need to detect a quantum of the gravitational field, a particle produced by the curving of spacetime itself, exchanged between two objects because of their mass, carrying the force of gravity directly. Nothing in the semiconductor experiment connected to any of that. This distinction matters enormously in science. A confirmed graviton would directly prove that gravity is quantized, that it operates through discrete packets at the smallest scales. It would place gravity inside the same framework as the other three forces, and open the door to a unified theory of all physics. The semiconductor result does none of that. What it does provide is a testbed, a place to probe graviton physics indirectly, studying how spin-2 quanta behave in a controlled setting where the signal is strong enough to measure. Every prediction the theory makes about graviton behavior can now be cross-checked against this system. If the theory predicts a specific scattering angle for spin-2 quanta at a certain energy, scientists can test that prediction using the semiconductor analog. If the prediction holds, confidence in the theoretical framework grows. If the prediction fails, the theory needs revision. This kind of indirect testing has been crucial throughout the history of physics. Scientists studied superconductors to understand quantum field theory long before they could measure individual particles directly. The analog systems taught them which parts of the theory were solid. The semiconductor graviton result fits into that tradition. A powerful tool, an indirect path, a genuine advance. And somewhere in that advance, a puzzle appeared that most popular coverage of the experiment did not mention. The spin-2 excitation they measured had properties that matched the theoretical graviton almost perfectly in some respects, and slightly differently in others. Those small differences might be noise. They might be artifacts of the experimental setup, or they might be pointing at something in the theory that is not quite right. That uncertainty is actually where physics lives. And one of the most unsettling pieces of uncertainty about the graviton has nothing to do with detection at all. It has to do with whether the graviton has even the tiniest amount of mass. Every particle in nature has a mirror image. The electron has the positron, same mass, opposite charge. The proton has the antiproton. The neutron has the antineutron. For every particle in the Standard Model, there exists an antiparticle with matching mass but opposite quantum numbers. When a particle meets its antiparticle, both annihilate in a burst of pure energy. Antiparticles are real. They are produced in particle accelerators, detected in cosmic rays, and used in medical imaging technology. Positron emission tomography, the scanner used in hospitals to image brain activity, works by detecting the antiparticle of the electron. The graviton breaks this pattern in a specific way. Physicists predict the graviton is its own antiparticle. That means the graviton and its mirror image are identical. The particle and the antiparticle are the same object. There is no separate antigraviton waiting to annihilate it. A few other particles share this property. The photon is its own antiparticle. The Z-boson is its own antiparticle. Particles with zero charge and zero internal quantum numbers that distinguish particle from antiparticle tend to fall into this category. For the graviton, the reasoning follows from its properties. It carries no electric charge. It has no color charge, the property carried by quarks. It has no weak isospin, the quantum number relevant to the weak nuclear force. There is nothing to flip when you go from particle to antiparticle. The particle and its mirror image are indistinguishable. They are the same thing. This has a consequence that disappoints science fiction immediately. Anti-gravity, as a physical concept, requires a particle that interacts with gravity in the opposite way that normal matter does. Something that falls up instead of down. Something that repels rather than attracts. In many fictional universes, anti-gravity drives spacecraft and enables levitation. The idea is that antimatter gravitons, or some gravitational analog to the electric charge flip between particles and antiparticles, would produce repulsion instead of attraction. But if the graviton is its own antiparticle, there is no flip to make. Gravity cannot be reversed by producing its antiparticle, because the antiparticle is already gravity itself. Every graviton, by definition, attracts. There is no version that repels. The universe, at the quantum level, appears to have locked gravity into a one-way force. This does not mean levitation is impossible. Through all mechanisms, other forces can still counteract gravity through electromagnetic repulsion or pressure forces. But the specific dream of a graviton-based anti-gravity drive belongs firmly in fiction. And yet the graviton's relationship to itself raises another question that is far from settled. The particle and antiparticle being identical assumes the graviton has exactly zero mass, because mass is one of the properties that distinguishes particle states from each other. If the graviton has even a vanishingly small mass, the situation changes. And what that would mean for the universe is one of the strangest predictions in all of physics. 0 is a very specific number. When physicists say the graviton is massless, they are not saying its mass is small or negligible. They are saying it is exactly, precisely, perfectly 0. No mass whatsoever. The same way a photon has exactly 0 mass, not a tiny bit. 0. That exact 0 is important. A massless particle must travel at exactly the speed of light. It can carry a force with infinite range. Its mathematical behavior is clean and follows specific symmetry rules called gauge invariance, the same mathematical structure that makes quantum electrodynamics work. But what if the graviton has a mass, even a mass so small it could never be directly measured? A mass hundreds of millions of times smaller than an electron, smaller than any particle ever detected. The consequences would be enormous, and they would reach across the entire universe. A massive graviton, any mass at all above 0, would travel slightly slower than the speed of light. The heavier it is, the slower it moves. This is a quantum mechanical rule tied to the energy-momentum relationship for massive particles. If gravity travels slower than light, then two events that happen at the same time, a gravitational wave produced by a colliding black hole, for example, would arrive at Earth at different moments depending on what kind of radiation you measure. Gravitational waves would lag behind electromagnetic waves. The delay, even tiny, would be measurable with precise enough instruments. Scientists checked this in 2017 when they detected both gravitational waves and gamma rays from a neutron star merger occurring simultaneously. The gravitational wave arrived 1.7 seconds before the electromagnetic signal, a gap explained by the different emission times of each type of radiation at the source, not by a difference in travel speed. The measurements placed an extremely tight upper limit on any possible graviton mass. The graviton cannot be heavier than a number that requires 32 decimal places to write. That rules out most massive graviton scenarios, but it does not rule out all of them. There is still a tiny window where a graviton mass could exist without contradicting any current measurement. A massive graviton would also behave differently over cosmic distances. The heavier the graviton, the shorter the range of the force it carries. A graviton with a non-zero mass would cause gravity to weaken faster with distance than the inverse square law predicts. At small distances, the difference would be undetectable, but across billions of light years, gravity from a massive graviton universe would look slightly different from standard gravity. Some physicists have proposed that the slight unexpected acceleration of the universe's expansion, currently attributed to something called dark energy, might actually be a signature of a massive graviton. The idea is controversial and not supported by current evidence, but it illustrates how even the smallest departure from zero mass would reshape cosmology. The current upper limit on graviton mass is the tightest ever placed on any particle property in history. The graviton is either exactly massless or so close to massless that the difference may never be measurable. But even that near-zero possibility opens a door to something completely wild. If gravity has mass, and if different gravitational frequencies travel at slightly different speeds, the universe might produce something nobody has ever observed. Gravity itself, bending into colors. White light enters a glass prism. Red, orange, yellow, green, blue, and violet light come out the other side, fanned out into a rainbow. This happens because different colors of light have different wavelengths, and different wavelengths travel through glass at slightly different speeds. The prism separates them. Each color exits at a different angle. The light that entered as a single beam leaves as a spectrum. Now apply that same logic to gravity. If the graviton has mass, gravitational waves of different frequencies would travel through space at slightly different speeds, just the way different colors of light travel through glass at slightly different speeds. A low-frequency gravitational wave would move slightly slower than a high-frequency one, or faster, depending on the model. Over billions of light years, that tiny speed difference would accumulate. A gravitational event that produces waves across a wide range of frequencies would send out a signal that spreads in time. The different frequencies would arrive at Earth at different moments, stretched apart by the accumulated effect of their different speeds. Physicists call this gravitational dispersion. The idea is that instead of a sharp, simultaneous arrival of all gravitational frequencies, you would detect a drawn-out signal with low frequencies arriving before high frequencies, or the reverse. The wave would have been pulled apart by the universe itself during its billion-year journey. The pattern of that spreading would carry the signature of the graviton's mass. Measure the dispersion carefully enough, and you could calculate how heavy the graviton is. Some researchers have extended this idea further. They describe the possibility of what they call a gravitational rainbow, a situation where gravitational radiation from a single source arrives at Earth as a smeared signal, each frequency arriving at its own moment, fanned out in time the way visible light fans out in a prism. Instead of a sharp chirp, as detected in 2015, you would hear a slow, stretched sweep. Current gravitational wave detectors have not observed this effect. Every merger signal detected so far has been consistent with massless graviton propagation, all frequencies arriving essentially simultaneously. Those observations tighten the mass limit further with each new event, but the next generation of detectors may push the sensitivity far beyond current limits. A space-based gravitational wave observatory, if built, would detect waves from mergers billions of light-years further away than current ground-based detectors can reach. More distance means more time for dispersion to accumulate. More distance means the gravitational rainbow, if it exists, has more room to spread out before arriving. If a massive graviton prediction is correct, the effect would eventually show up in data from those future instruments. Gravity itself, arriving at Earth color-coded by frequency, each shade of gravitational wave traveling at its own pace across a billion years of space. The prediction is vivid, the evidence does not yet support it, but the window remains open, and the next generation of sky-watching machines may close it in one of two ways. Either they detect the rainbow and rewrite physics, or they rule it out and strengthen the case for exact masslessness. One way or the other, the answer is written somewhere in the ancient light left over from the very beginning of the universe. 13.8 billion years ago, the universe existed as a dense, unimaginably hot plasma. Everything was packed together. Protons, electrons, photons, and gravitons, all crammed into a space incomparably smaller and hotter than anything that exists today. The universe was so dense that light could not travel freely. Photons collided constantly, bouncing off charged particles in every direction, trapped in a glowing fog. Then, around 380,000 years after the Big Bang, the universe cooled just enough for electrons to bind to protons and form neutral atoms for the first time. The fog lifted. Light was suddenly free to travel across space unimpeded. That ancient light is still traveling today. It has been spreading outward for over 13 billion years. It has cooled and stretched into microwave frequencies, invisible to the human eye, but detectable with the right instruments. Scientists call it the cosmic microwave background radiation, and it forms a faint, uniform glow, visible in every direction of the sky. This ancient light is a photograph of the universe at 380,000 years old. The tiny temperature variations in the glow correspond to tiny density variations in the early universe. Those density variations are the seeds of everything you see today. Stars, galaxies, galaxy clusters, all grew from those ancient fluctuations. And embedded in that light, at a level physicists are currently racing to detect, might be the fingerprint of gravitons from the very first moments of the universe. In the earliest fraction of a second after the Big Bang, during a period called inflation, when the universe expanded at an extraordinary rate, quantum fluctuations in the gravitational field would have been stretched to cosmic scales. Those stretched fluctuations are gravitational waves, produced when the universe itself was the size of a grapefruit. They would have left a specific imprint on the cosmic microwave background. The imprint takes the form of a polarization pattern. Polarization describes the direction in which light waves oscillate. A gravitational wave passing through the early plasma would have twisted the polarization of photons in a very specific way, creating a swirling pattern that cosmologists call B-mode polarization. Regular density variations, the kind that came from normal matter clumping together, produce a different polarization pattern with no curl to it. Only gravitational waves produce the swirling B-mode signature, and those gravitational waves, the primordial ones from inflation, would have been made of gravitons at the quantum level. Detecting B-mode polarization at the right scale would be the closest science has come to indirect evidence that primordial gravitons existed. Multiple experiments are currently searching for exactly this signal. Ground-based telescopes in Chile and the South Pole scan the microwave sky looking for those ancient swirls. So far, the signal has not been clearly detected. The search is ongoing, and the target is among the faintest signals in all of science. But if it is found, the universe itself will have handed physicists the oldest graviton evidence in existence. And that evidence, billions of years old, would land directly in the middle of the biggest theoretical argument in modern physics. String theory is the most ambitious framework in the history of physics. Its goal is total unification. One theory that describes every particle, every force, and every interaction in the universe using a single consistent set of equations. Physicists have been working on it since the 1970s, and it remains the leading candidate for a theory of everything, despite never having produced a directly confirmed prediction. String theory has a graviton problem. Specifically, it has a graviton solution. When string theorists first explored their framework, they ran into a strange result. The math kept producing a particle with no mass, no charge, and a spin of exactly 2. It appeared spontaneously in the equations, unrequested, as a necessary consequence of the theory's structure. Every version of string theory, regardless of how the other parameters were set, included this spin 2 massless particle. At first, this was seen as a problem. The particle did not correspond to anything physicists were studying at the time. String theory was originally developed to explain the strong nuclear force, not gravity. A mysterious spin 2 particle showing up was an inconvenience. Then, someone recognized what they were looking at. A massless spin 2 particle interacts with matter in exactly the way general relativity predicts gravity should work. The equations describing this particle's behavior are mathematically identical to Einstein's equations for space-time curvature. The particle they did not ask for was the graviton. This reversed the story entirely. String theory stopped being a theory of the strong force and became a candidate theory of everything, precisely because it could not avoid including quantum gravity. The graviton was not added to the theory. It emerged from the theory automatically, the way an inevitable consequence of the math forces itself into the answer. This is one of the main reasons string theorists believe their framework is pointing at something real. A theory designed to describe particle interactions at high energies accidentally produces a complete description of gravity as a bonus. The match is precise. The spin, the mass, the interaction rules all emerge from first principles. Remove the graviton from string theory, and the mathematical consistency of the entire framework collapses. The theory requires a closed string, and closed strings produce spin. spin-2 behavior and spin-2 massless behavior is gravity. You cannot have string theory without the graviton. This gives the graviton a unique status in physics. Every other particle is either confirmed by experiment or proposed to solve a specific observed problem. The graviton is required by a mathematical framework that arose independently and found gravity waiting inside itself. String theory has a weakness, though. Despite decades of work, no experiment has confirmed any uniquely string-theoretic prediction. No extra dimensions, no supersymmetric particles, no signatures that could only come from strings. The framework is mathematically rich and internally consistent, but it remains disconnected from experimental results. Some physicists see this as a temporary gap, waiting for instruments powerful enough to probe the right scales. Others see it as a deeper failure. Those others have built their own frameworks that make a far more radical claim. They say the graviton might not exist at all, and their reasoning is harder to dismiss than you might expect. Freeman Dyson was the one who proved a graviton detector was impossible. He also went further. In his 2013 paper, Dyson did not just conclude that gravitons are hard to detect. He raised a more fundamental question. Is there any experimental result that could ever distinguish a universe with a quantum gravitational field from a universe without one? He argued the answer might be no. If no conceivable experiment can tell the difference between two physical descriptions of the universe, then according to the philosophy underlying physics, both descriptions are equally valid. A theory that makes no testable prediction is not wrong, but it is not science in the traditional sense either. Some physicists took this argument and pushed it in a specific direction. Maybe the graviton does not exist because gravity is not a quantum force. Maybe general relativity is correct all the way down to the smallest scales, and space and time are genuinely smooth and continuous, with no discrete quantum structure underneath. This position is a minority view, but its supporters are serious physicists with serious arguments. Their case begins with an observation. Quantum mechanics was developed to describe matter, particles, and energy. Space and time are the arena where quantum events happen, the background against which particles move and interact. Why should the background itself be quantized? Why should space-time be made of discrete chunks just because the things inside it are? Einstein's general relativity treats space-time as a smooth geometric object. It curves, it bends, it stretches, but it does so continuously, the way a rubber sheet curves continuously under a heavy ball. There is no minimum unit of curvature in general relativity, no smallest possible bend. The field is smooth all the way down. Some researchers argue this smoothness is real. Gravity works differently from the other forces, because it is not a force in the usual sense. General relativity describes gravity as geometry, the shape of space-time itself. Electromagnetism and the nuclear forces are fields living inside that geometry. Quantizing the geometry is a category error, like trying to measure the color of a number. This camp includes researchers working on what they call semi-classical gravity, a framework where quantum matter fields live on a classical smooth space-time background. In this picture, the quantum behavior of matter affects space-time, but space-time itself remains unquantized. Semi-classical gravity works well in many situations. It correctly describes the radiation emitted by black holes, which Stephen Hawking derived using exactly this approach. It handles the behavior of quantum fields near massive objects. It breaks down in the same extreme conditions as full quantum gravity, near singularities, and at the Planck scale. But some physicists argue those breakdown points reveal the limits of physics itself, not a gap to be filled with gravitons. The graviton might be a particle that the math suggests, but the universe never actually made. That is a genuinely unsettling possibility. And the alternative framework that has grown up around it offers a picture of space-time so strange, it challenges every visual intuition you have built about space and distance. Imagine chainmail armor, not the smooth metal surface it appears to be from across a room. Up close, it is a mesh of interlocking loops, each link threaded through its neighbors. The surface looks continuous from far away. But zoom in and you find structure, gaps, individual units. The smoothness is an illusion produced by the scale at which you are looking. Loop quantum gravity proposes that space itself is like chainmail. At the scales you experience every day, space appears perfectly smooth and continuous. You can move in any direction, travel any distance, divide any path into smaller and smaller segments. Space seems to have no grain, no minimum unit, no underlying structure. But loop quantum gravity says that at the Planck scale, around 10 to the negative 35 meters, the smallest meaningful length in known physics, space is made of discrete interlocking units of area and volume. These units are like the links in the chainmail. They are the smallest pieces of space that can exist. You cannot subdivide them. You cannot pass through the gaps between them, because there are no gaps. They are space itself. In this framework, the curvature of space that Einstein described as smooth geometry becomes a counting problem. More links in a region means more space. Stronger gravity means the links are arranged differently. The continuous curves of general relativity emerge as the large-scale average of this discrete underlying structure, the same way a smooth metal surface emerges from the average of millions of interlocking rings. Loop quantum gravity does not require a graviton. Gravity in this framework is the geometry of space, and the geometry is discrete, but the discreteness comes from the loops themselves. There is no carrier particle exchanging between objects. Gravity is what the network of loops does when matter sits inside it. The framework has produced genuine results. It successfully predicts a minimum volume of space, which is a specific finite number that solves the infinite density problem that appears in general relativity at singularities. At the center of a black hole where general relativity predicts infinite density, loop quantum gravity predicts a maximum density, a bounce point where collapse reverses. It also predicts that the Big Bang was preceded by a big bounce, a previous contracting universe that reached maximum density and rebounded into expansion. The universe did not begin at an infinitely small point. It began at the smallest allowable loop quantum volume and grew from there. These are testable predictions in principle. The Big Bounce would leave a specific pattern in the cosmic microwave background, different from standard inflation predictions. Current data cannot clearly distinguish between the two, but future measurements might. Loop quantum gravity and string theory represent two completely different approaches to the same problem. String theory keeps the continuous background of space-time and quantizes the forces living inside it. Loop quantum gravity quantizes space-time itself and leaves the forces to be described separately. The graviton appears in string theory naturally. It has no place in loop quantum gravity. Both frameworks have produced genuine mathematics. Neither has produced a confirmed experimental result. And between them sits a simpler, measurable question that carries real observational stakes. How heavy could the graviton actually be? And what measurements have already eliminated? Science is full of questions where the answer is not yes or no, but smaller than this. The graviton's mass is one of those questions. Physicists cannot confirm the graviton's mass is zero. Exact zero is incredibly difficult to prove for any measured quantity, but they can set an upper limit, a ceiling above which the graviton's mass absolutely cannot be, based on observations of how gravity behaves across the universe. The current ceiling is extraordinarily tight. The graviton's mass, if it exists at all, must be less than 6 times 10 to the negative 32 electron volts. An electron volt is already a tiny unit of energy, far smaller than the mass of any known particle. 32 decimal places below that unit produces a number so small it essentially reads as zero in any practical context. For comparison, the mass of the lightest known particle with non-zero mass is the lightest neutrino, and even that is billions of times heavier than the graviton's upper mass limit. The graviton's possible mass is lighter than anything physics has ever directly measured. This upper limit comes from multiple independent sources of evidence. Each one approaches the problem differently and arrives at a consistent answer. First, gravitational wave propagation. When the neutron-star merger was detected in 2017 with both gravitational and electromagnetic signals, the two arrived within seconds of each other after traveling 130 million light-years. If the graviton had mass, it would have arrived later than the light because massive particles travel slower than massless ones at the same energy. The near-simultaneous arrival ruled out any graviton mass large enough to produce a detectable delay over that distance. Second, galactic scale gravity, the way galaxies rotate and the way galaxy clusters bend light, depends on how gravity behaves across distances measured in millions of light-years. If gravitons had mass, the gravitational force would weaken faster at those distances than the inverse square law predicts. The observed rotational curves and lensing measurements match standard gravity, setting another independent mass limit. Third, solar system dynamics. The orbits of planets are sensitive tests of gravitational behavior. Any significant graviton mass would produce measurable deviations in planetary orbits over centuries. Astronomical records stretching back hundreds of years, combined with precise modern measurements, show no such deviations. All three lines of evidence independently produce mass limits that cluster around the same extraordinarily small value. The consistency across different measurement types gives physicists confidence that the limit is real. What cannot be ruled out is exact zero. Every measurement has an error bar. Sitting below every error bar in every measurement performed so far is the possibility of a non-zero mass too small to detect. That window is fantastically thin, but it is open. Whether that window will ever close depends on a type of experiment that does not yet exist, and building it requires something more fundamental than new technology. It requires new physics. Every tool physicists use to probe the quantum world relies on one thing: electromagnetic force. Particle accelerators work by using electric fields to push charged particles to high speeds. Detectors register particles by measuring the electric signals they leave behind as they pass through material. Microscopes that image individual atoms use electrons and the electromagnetic interaction between those electrons and atomic nuclei. Nuclear magnetic resonance machines, the technology behind hospital scanners, use magnetic fields and the electromagnetic response of atomic nuclei. The entire toolkit of quantum physics runs on electromagnetism. That is not a coincidence. Electromagnetism is powerful enough at the quantum scale to produce measurable signals. A single photon can kick an electron hard enough to generate a detectable current. A single charged particle passing through a detector leaves an ionization trail that electronics can register. The force is strong enough that quantum scale events produce human scale signals. Gravity at the quantum scale produces nothing a human instrument can currently measure. A graviton passing through a detector the size of a building would not leave any detectable trace. The gravitational interaction is so weak that even the most sensitive electromagnetic detector cannot amplify it into a readable signal. This is a fundamental incompatibility. The tools are built for one force, the target uses a different force, that is 39 orders of magnitude weaker. To probe gravitons directly, physicists would need a detector that responds to gravitational interactions specifically, one where a graviton hitting the detector produces a signal strong enough to register. Nothing in current physics enables that. There is no material that amplifies gravitational interactions the way semiconductors amplify electronic ones. There is no gravitational analog to the photoelectric effect that could convert a single graviton into a measurable current. Building such a technology would require understanding quantum gravity first, but you cannot understand quantum gravity without experiments to guide the theory. The tools require the theory requires the tools. The loop has no obvious entry point. Some physicists have proposed indirect approaches. If gravitons affect quantum systems in subtle ways, for example by causing tiny decoherence effects in quantum superpositions, Then, extremely sensitive quantum interference experiments might detect a statistical signal of gravitational quantum effects without catching a single graviton directly. A few experiments along these lines are in early development. They look for minute changes in quantum coherence that would only appear if gravity is quantized. The predicted effects are extraordinarily small, and no result has emerged, but the approach is legitimate and represents the frontier of what experimental physics can attempt. The challenge is that any signal of quantized gravity in these experiments would require ruling out every other possible cause. Thermal vibration, electromagnetic noise, cosmic ray interference, and dozens of other effects all produce decoherence. Pulling a gravitational quantum signal out from that background requires experimental control at a level humanity has never demonstrated. New physics does not just mean a new discovery, it sometimes means a new kind of measurement that cannot even be imagined yet. Whoever breaks this problem open will have done something rarer than finding a new particle. They will have found a new way for humans to touch the universe. And the stakes of finding that way could not be higher, because the graviton sits at the center of an argument that has stalled physics for a century. Something falls into a black hole. Maybe it is a book, maybe it is a star, maybe it is a quantum of radiation with a specific energy state. Whatever it is, it carries information. The arrangement of its atoms, the state of its particles, the precise configuration of everything it is made of. Quantum mechanics has a rule: information cannot be destroyed. The total amount of information in a closed system stays constant. You can scramble it beyond any hope of reading it. You can spread it across 1 trillion particles, but the information exists somewhere, encoded in the state of the universe. General relativity says something different about black holes. Anything that crosses the event horizon, the boundary beyond which nothing can return, is gone, cut off from the rest of the universe. And after enough time, the black hole itself slowly radiates away through a quantum process discovered by Stephen Hawking, eventually evaporating completely. When it does, everything that fell in is gone. The information has been destroyed. Quantum mechanics says information cannot be destroyed. General relativity says black holes destroy it. Both theories cannot be right. This is called the black hole information paradox, and it is one of the deepest unsolved problems in physics. It is not a trivial technical disagreement. It strikes at whether quantum mechanics or general relativity is more fundamentally correct about the nature of reality. The graviton sits exactly at the boundary of this argument. If gravity is quantized, if gravitons are real, and gravity operates by quantum rules at the fundamental level, then the process by which a black hole evaporates might carry quantum information out in the gravitons emitted during that evaporation. The information would not be destroyed. It would be scrambled into an outgoing stream of gravitational quanta, unreadably complex, but in principle recoverable. This would save quantum mechanics. Information survives, encoded in the gravitational radiation the black hole releases over its lifetime. If gravity is smooth and classical all the way down, if there are no gravitons and space-time is a continuous geometric object, then the Hawking radiation cannot carry information in any clean quantum sense. The information problem remains unsolved. Some of the most prominent physicists of the last 30 years have argued that the information paradox can only be resolved by a quantum theory of gravity, that the paradox itself is a clue pointing directly at the incompleteness of general relativity, that black holes are not information destroyers, but the universe's most extreme information scramblers. The graviton is central to this resolution. A complete quantum gravity theory, one that properly describes what gravitons do near and inside black holes, would either solve the paradox or sharpen the contradiction to the point where the right answer becomes clear. Every physicist who has spent their career on quantum gravity has this problem somewhere in their thinking. It connects the undetectable particle to the largest philosophical question the universe has posed to science, and solving it would unlock something even bigger than the paradox itself. For most of physics history, theoretical discoveries eventually became technologies. Maxwell's equations for electromagnetism became radio, television, and wireless communication. Quantum mechanics became transistors, lasers, and computers. Einstein's mass-energy equivalence became nuclear power. The gap between abstract physics and practical technology is usually measured in decades. The graviton sits at a different place in that timeline. Finding it would be the beginning of a new era in physics, not an endpoint. A confirmed graviton would prove that gravity is quantized, that it operates through discrete packets at the smallest scales like every other force. That confirmation would validate the theoretical frameworks that predicted it and invalidate the ones that did not. It would tell physicists which direction to build a unified theory, a true unified theory of all forces, what physicists call a theory of everything, would describe every interaction in the universe using one consistent mathematical framework. General relativity unified into quantum mechanics. Gravity explained by the same rules as electromagnetism and the nuclear forces. The practical consequences of such a theory are impossible to predict with precision, because every previous theoretical unification produced applications nobody anticipated. Maxwell had no idea his equations would lead to smartphones. Einstein had no idea his photoelectric effect paper would lead to solar panels. The history of physics suggests that fundamental understanding consistently produces unexpected applications decades later. Quantum gravity might eventually point toward ways to engineer space-time directly, ways to generate or cancel gravitational fields, ways to understand the structure of the universe at its most extreme densities, ways to access or understand whatever is happening at the centers of black holes. These possibilities are speculative, separated from confirmed science by large gaps, but they are the natural extrapolation of what finding the graviton would mean, understanding the fundamental mechanism of gravity at the quantum scale for the first time ever. More immediately, finding the graviton would resolve the black hole information paradox, explain the hierarchy problem, and answer whether extra dimensions exist. It would confirm or destroy string theory, validate or eliminate loop quantum gravity, and close the chapter on 90 years of searching. It would also produce the most precise understanding of the first instant of the Big Bang ever achieved. The conditions at the origin of the universe require quantum gravity to describe. Every question about what existed before the Big Bang, what set the initial conditions, why the universe has the properties it has, requires the physics the graviton represents. Humanity has spent centuries learning to read the universe's language. The graviton is a word in that language that has been heard indirectly in every falling object and every orbit since the universe began. Finding it would mean finally reading that word directly. What remains before that happens is a gap that no current instrument can bridge. But the gap is not where science stops. It is exactly where it gets interesting. Every great revolution in physics started with someone noticing that the question everyone was asking was the wrong one. Before Copernicus, astronomers asked, "How do the planets move around Earth?" They built elaborate systems of circles within circles to describe what they observed. The calculations grew more complicated with every generation. The answers sort of worked, but they worked the way a lie works when you keep adding details to cover the gaps. The right question was, how do the planets move around the sun? One shift. Everything simplified. Some physicists believe the search for the graviton is the modern version of the geocentric model. Everyone is asking, what is the quantum particle of gravity? And the search has produced 90 years of mathematical sophistication and 0 confirmed results. The right question might be something no one has thought to ask yet. This is not a fringe position. Several serious physicists have articulated versions of it. The argument runs like this: quantum mechanics and general relativity are both incomplete descriptions of a deeper reality. The graviton is a prediction of quantum field theory applied to general relativity, but if both theories are incomplete, then their combination does not necessarily point at the right answer. It points at the best answer two incomplete theories can construct together. A truly complete theory of physics might describe gravity and quantum mechanics as two different limits of something more fundamental, the way classical mechanics and wave optics are both limits of quantum electrodynamics. In the deeper theory, the concept of a force carrier particle might not apply to gravity the way it applies to the other forces. Gravity might emerge from something more structural, more geometric, or more abstract than a particle exchange. Some researchers working in this direction use ideas from quantum information theory. They argue that space-time itself might emerge from the way quantum systems are entangled with each other. Space is not the background inside which quantum events happen. Space is the pattern of entanglement between quantum degrees of freedom. Distances between points reflect the strength of quantum correlations. In this picture, asking where the graviton is resembles asking where the pixel is in a painting. The painting is made of pixels, but the meaning of the painting does not live in any single pixel. The structure emerges at a higher level. Gravity in this view is the emergent geometry of quantum entanglement, and a single graviton would be like one pixel in an image that only makes sense at larger scales. This framework is speculative but mathematically active. Researchers have shown that specific calculations connecting geometry to entanglement work in ways that match expectations from general relativity. The direction is promising enough that serious funding and serious minds are engaged. The unsettling implication is that the graviton search might be correct in detail but wrong in spirit. Finding the graviton would confirm quantum field theory applies to gravity. But the deeper structure of gravity might be something that the graviton only approximately describes, the way a particle approximately describes what is really a quantum field. And a field approximately describes what is really a geometric structure of entanglement. Physics has shifted frameworks before. Each shift expanded what was knowable. The next one might make the graviton look like a stepping stone to something no one has named yet. The instruments that will push graviton science forward in the coming decades are already being designed. On the ground, upgrades to existing gravitational wave observatories are underway. The current detectors measure space displacement smaller than a proton's width. The next generation aims to improve that sensitivity by a factor of 10 to 100 across the frequency range. More sensitivity means detecting mergers farther away. More distant mergers means more time for any subtle graviton effects to accumulate before the signal arrives. More events also means better statistics. The mass limit on the graviton has improved with every new detection. Dozens of events give a better limit than one. Hundreds give a better limit than dozens. The more merger signals researchers collect, the tighter they can squeeze the graviton's possible mass, pushing the upper limit even closer to zero. In space, a mission called the Laser Interferometer Space Antenna has been approved and is in development. It will consist of 3 spacecraft arranged in a triangle, each side around 1.5 million miles long. The scale is incomprehensible by ground standards. The lasers between the spacecraft will measure length changes smaller than a proton's width across a baseline of 1.5 million miles. This design detects gravitational waves at far lower frequencies than ground observatories can reach. Low-frequency waves are produced by much larger and more distant sources. Supermassive black holes millions of times the mass of the Sun, merging at the centers of galaxies. White dwarf binaries spiraling together over millions of years. These events are more powerful and more distant, meaning any graviton dispersion effect, if it exists, would have even more distance over which to accumulate. The Space Observatory could constrain the graviton mass by another factor of 1,000 beyond current limits. If a massive graviton exists in the still open window, this instrument would find it. If the window closes and remains empty, exact masslessness becomes the only viable conclusion. On a completely different front, quantum gravity experiments are moving from thought experiments to laboratory proposals. Several teams are developing quantum mechanical systems, tiny suspended masses held in quantum superpositions, designed to test whether gravity can entangle two quantum objects. If gravity entangles quantum systems, it must itself be quantum. A classical, smooth gravitational field cannot produce quantum entanglement between two objects. The detection of gravitationally induced entanglement would be the first direct evidence that gravity is quantized, the closest thing to catching the graviton without catching it. These experiments require maintaining quantum coherence in objects large enough to have measurable gravitational interactions. Current quantum systems are either tiny, where gravity is negligible, or large enough to feel gravity, but too warm and noisy to stay quantum. The middle ground is technically brutal. Several groups believe they are within a decade of bridging that gap. The experiments are being designed, the funding is being sought, the theoretical predictions are being sharpened. The next 10 to 20 years represent the best chance in the history of science for humanity to finally close in on the ghost. 90 years. That is how long the graviton has existed as a named theoretical object, without a single experimental confirmation. 90 years of papers, calculations, debates, and revised estimates. 90 years of the two greatest theories in science refusing to share the same equations. The graviton is the particle sitting at the center of that refusal. Physics has two descriptions of reality. One describes the very large, the other describes the very small. Both work extraordinarily well within their domains. Both break down at the boundary. And the boundary, the place where quantum mechanics and gravity must both apply simultaneously, is the most extreme environment in the universe. The centers of black holes and the first instant of the Big Bang. Those two locations are not abstract. They are real places. The universe went through one of them at its origin, and black holes sit at the centers of most large galaxies, including our own. Physics has no working description of either. Every attempt to describe those locations requires the same thing: a quantum theory of gravity, a framework where space-time behaves by quantum rules, where the smallest unit of gravity can be identified, counted, and calculated. The graviton is the cornerstone of that framework. One confirmed graviton would do more than fill a gap in the particle list. It would prove that gravity and quantum mechanics speak the same language at the fundamental level, that the universe runs on one set of rules, from the largest scale to the smallest. That the split between relativity and quantum mechanics is a practical limitation, not a fundamental one. That proof would release 90 years of blocked progress. Questions that cannot currently be asked would become answerable. The physics of the Big Bang's first moments would open up. The information paradox would resolve in one direction or another. String theory would be confirmed or eliminated. The hierarchy problem would have a framework for a solution. The graviton might already be confirmed indirectly by the time you hear this, through the gravitational entanglement experiments, through primordial B-mode polarization, through dispersion patterns in distant merger signals. The confirmation might come from a direction nobody currently predicts. The history of physics is filled with discoveries that arrived through a window nobody had thought to open. What makes the graviton uniquely compelling, even among the great unsolved problems of science, is its invisibility. It is not hiding because we lack the technology, though we do. It is hiding because the laws of physics build barriers around it. The particle that carries gravity is protected by gravity itself. The force it transmits is the force that makes it undetectable. The universe carries its deepest secret in the particle that shapes everything you have ever seen or felt. Every orbit, every falling object, every structure in the cosmos, all of it governed by a force whose quantum carrier remains, after a century of searching, completely beyond reach. The biggest argument in science has one answer, and the answer is one particle. We have never seen it. We have never stopped looking.